Let's go ahead and take a look at a phase plane of this model right here. There is an application here that you can actually download and do a lot of things at once, though it may or may not work properly for you. So I'll show you another applet that will be able to do this really well. And this is our old slope field grapher. So that's the same link as we used to generate slope fields. So we're going to enter in dx dt equals 1.7x minus 1.1xy. So let's go ahead and do that. So from this applet, first of all, we need to drop down, and instead of one ODE, we want to plot a system. And so you can change the variables here. If we use R and F, usually that's used to represent rabbits and foxes. So we'll just go ahead and do y versus x. And of course, we need to update our equations to reflect 1.7x minus 1.1xy. Now, we might get an error, and you'll see that this is kind of yelling at us. And the reason it's doing that is because we need to put multiplication signs, at least between the variables. So if we put that multiplication sign there, it's a good practice just to always have multiplication signs, because in some languages, you actually need to explicitly write it out. Then we'll put in dy dt equals negative 0.8y plus 0.6 x times y. Okay, so there we have the system, and we'll click back off of this right here. Now we'll change our window settings a little bit because we really want to focus on the first quadrant. We are dealing with some sort of species, let's say. So maybe we'll go 0 to 4 and 0 to 3 on y. And one thing that's interesting to note here is if you click anywhere on this phase plane, it generates the trajectory, which kind of follows, and it looks somewhat like an oval, right? It has this kind of egg shape and this circle of life type of thing going on here. And this is probably the most reflective thing of the concept of the circle of life, that basically there will be a birth and death cycle taking place. And we'll soon come to see that right in the middle of this is one of our equilibrium points. In fact, if I start to click trajectories, you can see that that's, maybe you can't, 4/3 and 17/11, I believe, was our equilibrium point. That is actually right in the middle there. Now let me go ahead and delete these trajectories, which we can do by just simply clicking on initial points, clear all curves. I'll uncheck that, and I'll just select one of those. Okay, now as with ordinary differential equations, individual, single, 1 ODE models, we can actually generate a table of values. Okay, so we'll get our table of values. Now this is right now based upon Runge-Kutta 4. You can change this to Euler's method, but Runge-Kutta 4 is optimal. And if you actually click on this, you'll see that the difference here is that we have a K1 for X and a K1 for Y and a K2 for X and a K2 for Y. This is the same concept as Runge-Kutta for ordinary differential equations. Everything just has to get generated 4 times, once for X and once for Y. So our 4 slopes concept for X, our 4 slopes for Y, they of course feed into each other because dx dt depends upon both X and Y, and similarly for dy dt. So as you can see that as you kind of go down the table, you get this little arrow over here that shows you where we are currently. And this will generate for lots of points in time, namely because, as you notice, we just kind of keep going around the circle, right? So time is not in this graph. That's an important thing that we want to remember, is that we are looking at a relationship of how X and Y co-vary. Now, if we actually want to see the time, X versus time and Y versus time graphs, we can do that by clicking on this time plot feature. The time plot feature, very cool, shows you the point over here in the phase plane where we are. Okay, so X is just above right around 1.5. Y is right around 1.825 or so. And then as we circle around that trajectory, we see that, okay, right now y is increasing slightly, right? Y is going up, and X is decreasing because we're moving to the left. But now we notice that that black point in our phase plane over here is actually moving down, but X is starting to increase, moving to the right, and we're moving up. Now we're moving to the left, but we're still moving up. And now we're still moving to the left, but we're moving down. And you can see how those populations covary, and you get this sinusoidal, this sort of periodic function going on, which is super neat to see. So we can do a variety of things in here. We can actually change this to just going and generating Euler's method. Now with Euler's method, the one thing you're going to notice is you get something very bizarre taking place. You get kind of these weird looking spirals. And that has to do with the fact that Euler's method is very sloppy, especially for systems. The error is getting vastly huge. What you're seeing here is because we get small deviations in the step size, when we come back around, we expect our kind of egg shape to link back to the starting point, but it doesn't because of enough error that we actually start spiraling outwards, and we get this crazy-like behavior. So we generally don't use Euler's method for systems of differential equations. It's best just to go with Runge-Kutta of 4. And of course, you can mess with that step size even further. And let's just say, we're interested maybe at time 10, what's going on. Okay, so notice that at time 10, the step size of h equals 0.1. We have an x value of 1.75 and 1.56. If we change that to 0.01, let's see what happens. Time 10, assuming our table will even go out that far, because it's generating a lot of ordered pairs here. It does go out to time 10, nice. 1.75, 1.56. You can see that that's pretty accurate, even compared to a step size of 0.1. Again, one of the major advantages of using Runge-Kutta of 4.